Okay, welcome back to our engineering economics video on annual equivalent analysis. So we started example problem 6.1 in the last video, and we almost made it to the end, but not quite. So what we did is we set up this table that had a column for a number of years, and the problem statement said that we were going to install some new boilers, I think, that are going to save us money in electricity and coal. So we had two different sources of savings, which can be thought of as revenue, and they each increased on an annual basis, but at different rates. The electricity increased at 4% per year, and the savings in coal increased at 5% per year. And then we had this initial investment of $159,000. So we set up this column here as the total or sum of the cash flow, the net cash flow, that essentially is just the sum of each of the previous three columns. So we have an initial outlay of cash of $159,000, and then this is the combined savings that we're going to experience on an annual basis throughout the life of the project. So what we then did is set up a column here for the future value of all of these. And I had to make sure to include a negative sign here because Excel likes to flip the sign of future and present values. So if we put in a present value of negative, it would return a positive value here. But we don't want that in this case. We want for our negative costs to still be negative and our positive revenues to remain positive. And so also I should point out we use the 10% rate as specified in the problem statement. That's the minimum rate that the company wants to receive for their investment. And the number of periods, I had to put in a little formula here. I put in 12 minus the n value because this initial investment collects interest for 12 years, not 0 years. And then it goes 12, 11, 10, 9, 8, 7, so on and so forth. So rather than creating an additional column with those values in it, I just wrote in a little formula here, 12 minus 0, 12 minus 1, 12 minus 2, and so on. And so that finds me the future value of all of these. So the future value of our investment is basically telling us our opportunity cost. This is how much it costs us to invest in this project, because it doesn't just cost us $159,000. It costs us $159,000 plus 12 years worth of revenue at 10% that we could have been earning if we had invested that money in some other project. And then for all of the other positive income values, this is telling us what it would be worth. For instance, here, $54,950, if we took this money and again invested at 10% for 11 years, and the next value investing it for 10 years, and so on. What would all these values be worth? And we can tell that we did it right because when we get down to the end here, the 12th year, that amount of money that we save in the 12th year, its future value is equal to its face value. It doesn't increase at all because it hasn't had any time to gather interest. So here we have all of our future values in this last column, and at the bottom I've summed it up. I've just added all of these values. So this is telling us right here, this is the total future value of this project, $959,000, which is above and beyond our 10%. So let's find out what that is on an annual equivalent basis. So we know the total amount, but let's spread that out over 12 years. Now, it is not just as simple as taking this value and dividing by 12. We can't do that because of the fact that all of these values are earning interest over time. And so it's not going to divide evenly by 12. it just doesn't work that way. Instead, what we need to do is use a payment function to find. Think of it almost as if this is the amount of money we're going to borrow, and we're going to pay it off in annual installments like a loan. It's a similar concept. This is the future value of this project. At the end of the project, that's what it will be worth. We want to take that and spread it out evenly over 12 years to find out how much it's worth per year. So we can use a payment function. Again, we're going to use that 10% rate, 0.1, or 10%. The number of periods is 12. There is no present value. Instead, we have a future value of this 959,000. But again, I'm going to make that negative because Excel, when we use those Excel functions, it flips the sign, and we don't want it to flip the sign. We can see here that our future value is positive, so we want to spread that out over 12 years. It's not going to magically become negative. It should remain positive. And there we go. That answer right there is our annual equivalent value of $44,859.21. So if we invest our $159,000 and we get all of this savings, that is equivalent to $44,859, and that's $44,859 a year above our 10% return. Okay, so that this is not telling us the total revenue of the project on an annual basis. This is based on that 10% value. This is telling us how much more we would get than a straight up 10% investment. So because we get this positive value that's greater than 0, that's telling us that this is a project that this company would want to invest in, because we are going to receive more than a 10% return. So I touched on this earlier. Why would we want to do this annual equivalent analysis? Why wouldn't we just simply do a present value analysis? Isn't that simpler? It is, but if you're comparing two different projects that have different lengths, one is a relatively short project, another one is a relatively long project, it can be difficult to compare those two projects to determine which is the better option. So this annual equivalent analysis levels that playing field. It puts both values in terms of an annual amount, and then we can clearly compare project A to project B in order to determine which one is going to make us more money. It can also help us when we are trying to decide whether to buy or rent something. If we take the cost of buying and owning something and then find an annual equivalence, we can compare that to what it might cost to rent or lease that same equipment. And again, it's a good type of analysis to use when you might have the revenue or costs associated with the project are somewhat imbalanced. For instance, the project is potentially profitable, but those profits don't come towards the end of the project. This type of analysis takes those profits and kind of evenly spreads it out over the life of the project, so you can get a better idea of its worth when you look at it on an annual basis. So something that's closely related to the annual equivalent worth or value analysis is annual equivalent cost analysis. So this essentially is when there really is no income. It's really just cost. So you're not necessarily looking at making money, you just want to try to spend the least amount of money. So this is a type of analysis that can be used for two different operating models or two different systems in which there are going to be costs. You know that it's going to cost you money, but it's a necessary cost of doing business. However, you would still like to minimize that cost and keep it down. So we need to separate our costs into two different categories when we consider them. There are operating costs that occur on a regular basis, like an annual basis. You have to pay over and over again. And then there are capital costs. These are costs that typically are one-time only costs. So we talked in class about building a factory and then operating that factory. So the capital cost would be the cost of building the factory, and then the operating costs are how much it costs to keep that factory running year in and year out. So I think I'm going to stop this video right here before we get into the next example problem so that I can do that next example straight through without being interrupted. So I'll stop here and I'll see you in the next video.